Hello everybody. This lecture video includes questions related to hydrostatic pressure calculation and application of Bernoulli's equation. Before we solve question number 1, which asks it to find hydrostatic pressure at a point using the hydrostatic equation, what is the definition of hydrostatic pressure? Hydrostatic pressure is a pressure in a liquid at a given depth. Alright then, let's look at the question. This question tells you the pressure at point 1, which is 195 kilopascal, in a vessel filled with the fluid density of 1.240 gram per centimeter cubed, and ask you to find the pressure at point 2, which is 2.47 meter above point 1. And they are filled with the same fluid. We need to show pressure in unit of a kilopascal to the nearest 3 sigfix. We can calculate the pressure in a liquid at a given depth using hydrostatic equation, which you can write it as P1 is equals to P2 plus rho GH, and P1 will have higher pressure than the P2, and rho is the density of the liquid, and g is the acceleration due to gravity, which is 9.81 meter per second square. And last but not least, h is difference in height or depth. There are two ways to solve P2 using this equation. First one is calculating the pressure using the SI unit, which I think we are more familiar with, but it takes a little time to do the conversions. Second way that I will introduce later is simpler, but we need to understand the relationship between units of variables by doing dimensional analysis. Let's find the pressure using the first method. Since the gravitational acceleration is given as meter per second square, and we have P1 value that is given to you as kilopascal, so that can be 195,000 Pascal. And we can convert that density, which is rho that is equals to 1.240 gram per centimeter cube. And we want to convert that into the SI unit, which is kilogram per meter cube. So we need to multiply the conversion ratio, which 1000 gram is a kilogram, and 100 centimeter is a meter, but we have 3 of those, so we need to cube it. And after you do the calculation, you'll have 1240 kilogram per meter cube. You will see the density unit of gram per centimeter cube quite often in this pressure question. And if you want to use the first method, it is not a bad idea to memorize this conversion here. that you just need to move the 3 decimal places to the right to get kilogram per meter cubed from gram per centimeter cubed. Now, let's plug in those converted value into the equation to find the pressure at point 2. P2, that is equals to P1 minus rho GH. The P1 value is 195,000 Pascal minus the density that we converted is 1,240 kilogram per meter cube, and gravitational acceleration, that is 9.81 meter per second square, and the difference in height or depth is 2.47 meter, which you can calculate it as 164,953.93 Pascal, which rounded to 165 kilopascal. In fact, we can find the same answer without doing any of the unit conversions, and let's look at the units closely with dimensional analysis to find a simpler solution. Pascal is derived unit by multiplying kilogram per meter cube and meter per second square and a meter. And to get a kilopascal, we need to divide Pascal with 1000, which you can write it as times 10 to the power of negative 3. From above density conversion, we needed to move 3 decimal places to the right to get kilogram per meter cube, and this is same as multiplying 1000, and we can write it as 10 cubed. So we can rewrite this kilogram per meter cube with gram per centimeter cube times 10 cubed, and this 10 cubed and 10 to the power of negative 3 get cancelled. And the key notes to remember is that the units get cancelled nicely with density, gram per centimeter cube, and pressure unit, kilopascal. And in fact, we didn't have to do any conversions from the first place. We can recalculate P2 using the same equation, and that is 1.240 gram per centimeter cube times 9.81 meter per second square and 2.47 meter. And this will give you the answer of 165 kilopascal as well.